Recording is on.
Hello, everyone. Welcome to, I think, meeting number 7 of the Reading Club for the book Mastering the Lightning Network. We're reading Chapter 8 this week, or we read Chapter 8, and we're just gonna see where it goes. I read it. I finished it this morning, and I thought it wasn't as hard as the previous ones. I think the 6 and 7 had more meat on the bone, I thought, than this one. Or not, just like, yeah, were a bit harder for me to get, whereas this was the idea that you're basically, finding routes across which you push a payment, the money gets transferred from one to the other, to the other, to the other, until it reaches destination. And
Yeah, I think it requires different kind of thought pathways, like in terms of like which is harder and which is not. This is very much in the I don't know. I know that there's just like people who, within the realm of computer science, really specialize in thinking about this like kind of network connection mentality, how many nodes you have in a network and how many of them are connected and what's the optimal path through the network. It's like kind of like I think I mentioned on like a previous call. It's like a long time kind of networking challenge, figuring these things out. And I imagine for someone who spends a lot of time thinking about that kind of stuff, this chapter is probably fairly trivial. And for someone who's not, this would probably be a little bit more of a challenging chapter.
I didn't really, since I haven't read it, I can't say, but did they get into the actual protocol that they use? Is it just sort of a least cost route, or like, did they talk about which?
No, it doesn't go into what is used to find that path, that's okay. I think another chapter. This is where if you've established that this is the optimal route or the route you want to take, how do you ensure that this route happens atomically?
I see.
That's basically the gist of the chapter is how do we make this either completely succeed or completely fail? And what are the requirements for this to happen? I think an important concept is the idea of like the hash and the preimage. So, that depends if people are familiar with that, but this act of like revealing a preimage, you've had the hash maybe for a long time, and I can show you what it was the initial sort of like message or number or whatever that computes to that hash. Revealing the preimage is like an important part of that chapter.
I think one thing. Yeah, go ahead, Alexa.
No, go ahead, Raj.
I think the one thing that this chapter did very interestingly is it basically broke down the HTLC contract in English. So basically what happens, like if you translate the contract, like all those signatures, hash preimages and time locks into English, and it says something like a contract clause as long as like a 2-3 sentence. So that's a cool thing that I learned here. Like it basically reduces into a very simple English verbal contract between two parties about how their coins are to be retrieved and when their coins will pass to either to them or to the other party. So that's another cool thing. And I was also like going through some of the presentations by René Picard. He's working on the routing part of the Lightning Network, and he came up with this new idea called the JIT routing. And so one thing that he mentioned is basically that it's not, routing is hard in Lightning. It's not because we don't know how to pathfind. It's because there is no path to find, because the way Lightning Network is designed, it hides certain data about the graph of the network transaction that you cannot use to make a proper pathfinding algorithm. So if you have all the data, then pathfinding is really simple. Computer science people have these algorithms that they can run and get the least distance path or the least cost path in certain ways. But in Lightning, because we don't have the complete representation of the network, specifically we don't have the view of the balances of each side of individual channels, and these balances are required to construct a path from you to the receiver. And because this balance is not available, so what they do in Lightning is basically they cannot guarantee like whatever the path a transaction took, that's the most optimum path. What it does is like it tries to probe path along multiple routes that it can find, and the first thing that succeeds, that's it, that's the path that through which the protocol went. It might not be the least distance path, it might not be the least fee path, it's just a path that worked. And that's kind of like the only way they have right now in order to like circumvent this problem of not having a very complete and detailed image of the transaction or network graph right now.
Makes sense. So I was wondering, maybe since the HTLCs were such a important part of this chapter, maybe we could pull up the diagram on a screen share and talk about that together. Be curious to understand this better.
Yeah, that would be nice.
Okay, can everybody see my screen okay?
Yep.
Let's see, I think I'm trying to figure out what browser it is. Yeah, there we go. Okay, so I believe this is where the HTLCs are introduced. Okay, Alice gets a payment hash from DNS. We see Alice. So basically, I remember this equation from back in chapter 3, I think, where they first introduced the concept of a preimage. I think of the preimage in a sense in my mind a little bit like the seed that's used to create a private key, even though this is nowhere near as complex. But so the hash and the preimage are related, but they're two different things. So the preimage is random, and then it gets input into the hashing algorithm, and then it creates H. So Alice here is requesting an invoice on Dina's website. So Dina generates a secret R, creates the hash from that, and then sends the hash back to Alice's node. What else do you think? Thunderbishki, do you think you could walk us through this a little bit?
Yeah. So I think that at this point, if you think of Alice, she has sort of like the final answer, right? She has the hash of this secret, and Dina has the secret itself. And so if she could get the secret, she would know that this secret has been passed from Dina all the way to her. And this idea is really important. This is what's happening. Dina is going to pass on that secret from herself to Chan, and then Chan to Bob, and then Bob to Alice. And once Alice sees the secret and that it matches to the hash, she knows that indeed the whole root's sort of like succeeded or has worked. And yeah, that's kind of what's happening. I'm wondering if
okay. So I think I'm starting to understand this a little bit. And again, I skimmed the chapter this week because I'm low on time, so forgive me. But so in this scenario here, Alice is trying to send money to Dina, correct? But she doesn't have a channel with Dina. She's trying to route the payment through other people's channels. Am I understanding that correct in this example?
That's right.
Okay, so she's going to send from Alice to Bob. Bob will send to Chan, and then Chan will send to Dina. And then the kind of challenge here is that Alice, there needs to be a way that she knows that the payment was successfully routed to Dina, that Bob or Chan in this process didn't just keep the funds and not successfully complete the payment. And
yeah, one thing I think another important thing that here is like Dina doesn't give the secret to Alice, it comes to Alice, but what Dina does is like Dina gives it to Chan, and Chan gives it to Bob, and Bob gives back to Alice. So by the time when it reaches Alice, Alice knows that Dina has already got paid. So Alice only negotiates the channel between Alice and Bob. So Alice and Bob now can settle their HTLCs together. So it kind of like goes from the receiver to the origin backward.
Yeah, I guess I'm a little confused at the moment, and maybe the text clarifies this much more. But I'm confused about how Alice's node is able to do anything actionable with the hash if she doesn't know the secret, if the secret is generated over here.
Now that's a nice question, and I think like one meta way to think about it is like when Alice is creating all these HTLCs, magics, and stuffs. He doesn't have any other communication with Dina, right? So she doesn't know whether Dina is receiving the coins or not. All Dina told Alice is like, hey, take this payment hash. If you find somewhere the preimage of this payment hash, know that I have given up that secret. And the only reason I will given up this secret is because I have got the payment.
Gotcha. So I bet some of these other images are going to clarify that a little bit more. So this image isn't telling the full story right here. The magic kind of happens later when Dina gives up the secret.
Yeah. It's just Dina promised that I will give you the secret if you make the HTLC magic with Bob and Chan and other.
And I can maybe I have another browser tool that I use for that. So if you want, I can take the screen share from you.
Yeah, that'd be great. Let me. There you go. Yeah, this annoying thing where Jitsi crashes every time I exit a screen share. I'm trying to figure out how to solve this bug, so sorry about that. But
yeah, I think it's not letting me screen share either.
Should be able to. Do you see the button at the bottom of your screen?
Yeah, it's like.
Oh, I'm going to kick other Steven out of the room. Will it let you know?
It's my, I think it's my computer, my preferences.
I gotcha.
Security thing.
Yeah. I'll just have a quick look.
Okay, but I'm starting to look. I'm scrolling through while you're looking into that. I'm scrolling through the rest of Chapter 8 and looking at some of these infographics, and then I see there's another graphic here where we show Dina's secret R essentially being passed back to Chan. And
I took a few notes. Maybe it would help if we look at some of the things I highlighted on it. I don't know. I haven't gone through it, but
yeah, that'd be great.
I don't know if that will totally mess up what Thunder Biscuit's trying to do, though.
No.
Can you share your screen, Alexa? Or however you wanted to share these.
So I don't know. I highlighted a few things in different colors, so and some notes. So hopefully that could help. I don't know. I think we're talking about routing a payment, and it's about finding a path of well-funded channels. That's what I got. That was kind of the main thing in here. And you're trying to pay like 50,000 sats to Dina for streaming a game, I think. So when we look at it, Alice doesn't have any direct channels to Dina, so she has to route through Bob and through Chan. And what I got from this is that routing nodes any node can route payments. No one can steal funds while routing. You can charge a fee, but you don't have to. And you only know who you're connected to, right? You don't know. it's a private channel. Let's see. And then of course we have the hash time log contract. It describes the difference between routing and pathfinding. Finding, where routing is the actual process that is happening, and pathfinding is when you're kind of looking at it or listening for the channels to see what route you could take. And that's kind of the main difference between them. I hope I'm not scrolling too badly here. Let's see. So again, if we look at the diagram, she wants to pay Dina, but there's no direct channel. And you have to pay attention to the capacity of the channels, of course, to see how you can route it and whether you can route it or not. Let's see. Physical example of routing. And in here, they switch to paying 10 gold coins. Like, how would you go into giving 10 gold coins to Dina? And one of the ways that they put it is that, of course, Bob and Chan have to get a fee. So once we get to this point, hang on. Apparently, I didn't take many notes on this one. But let's see. The way that it starts is that you take into account the fee, right? So you have 12 gold coins that you send to Bob, and then 11 gold coins that you send to Chan, and then finally Dina gets 10. It's kind of the way to take into account the fees. And I don't know, he describes it as an escrow service. And the receipt or proof of payment could take the form of a secret that only Dina knows.
So the reason they need an escrow is because, like, if Alice pays to Bob, like, Alice doesn't have any guarantee, like, if Bob will not run away with that money. So Alice says, like, says to Bob, like, hey, I'm not giving you the money directly. Here it's in escrow. If you show the proof that the payment happened, so you get the money, otherwise I get it back.
Thank you, Raj, for explaining that. Otherwise, it doesn't make sense. Yes. And the way that they describe this is that there's a payment hash and a payment secret. And obviously, the payment hash has the secret, and the payment secret unlocks the secret. That's kind of how this thing is. Hang on. What is this one? Let's see. Dina will create the payment secret via an external channel. Now, they keep referring to this as an external channel because when they send the invoice, it happens separately outside of the Lightning Network. So Dina has to share the hash with Alice, and in order for kind of the process to begin.
So I guess in that upper dotted line there, we can imagine that that's something like, say with the Bitcoin Smiles campaign the other day, and they have a BTC Pay server set up, and you go click to donate to it, and it generates a little Lightning invoice right there, and I don't have a direct channel with the Bitcoin Smiles BTC Pay server, so that dotted line would essentially be like me, getting that invoice from their website, and I would be sending from Alice to Bob to Chan to Bitcoin Smiles.
Yes, and the way that this chapter was kind of set up was that they kept rewriting kind of what the contract would be. So that you'd know the things that you needed to add in order for there not to be any cheating or stealing. And as you go through the chapter, there's something else that they add. In this case, is that this contract now protects Alice from Bob not forwarding to Chan, and protects Bob from not being reimbursed by Alice, and ensures that there will be proof that Dina was ultimately paid via the hash of Dina's secret. There'll be a few more things here that are introduced, though. And maybe, Raj, if I missed something, please let me know, because I'm sure I'm missing some important things here. And the thing here is that they were talking about what would happen, and let me see if I understood it right. What would happen if Dina just released the secret, but somewhere along the line, the secret wasn't passed? I think that's kind of what they were talking about. That any one of them could choose not to release the secret and somebody's money would be stuck somewhere. So that they said that the way to solve it was to add a deadline or a time lock. And if like the contract isn't kind of followed by everyone within that amount of time, then they just get the money back. And that's kind of the main point of that, and that's the atomicity, the all or nothing of the. You either all of them get it or none of them kind of get it. Let's see.
Yeah, I think this is where it goes like describing into the HTLC thing, like hash and time locked. So this is basically a kind of like financial contract that are locked by two clauses. One is it's a time lock, one it's a hash lock. The hash lock says like if the image of this hash is revealed in some way, then the contract passes through. If it doesn't happen within this particular time, then the contract falls back and everybody gets their money. Now instead of an escrow, we have like Bitcoin blockchain to do that mitigation, and then this contract can then be translated into a Bitcoin script, and that's basically is Lightning Network.
Yeah, that's very good. Thank you, both of you. So I'm curious about, so with the HTLCs, that makes sense. You need to provide the secret in order to get your funds out of escrow, or you need to provide the pre-image, the secret, to get your funds out of escrow. I'm guessing there would be, since essentially each node is, creating pre-signed Bitcoin transactions between each other, between their channel partner, I guess there would be an HTLC in every single transaction between each of the nodes. Am I correct in my thinking?
That's right. I think that everybody along that path only deals with the next person. So they don't necessarily care about how deep it goes, or if there's like another 100 paths after. Chan is just thinking, I can, I'll receive on one side and then I can decide to give out on the other side. And it just tends to be better for both parties, for all parties to do exactly that, to stay off chain. But if anybody along that route is like not there, or everybody has like two ways to basically resolve it, right? You can go on chain if something happens, or you can stay off chain and just decide to move. And you can either, so the way you do this is you either wait the 24 hours and then you break the contract, you break out, or you grab the secret and you pass it along. And when you pass along the secret, the money gets exchanged for the secret. And maybe this is a good time for me to screen share now. I think it'll work.
Yeah, go ahead.
Yeah, that was very good, Alexa. Thank you. Schooling those of us that didn't do our homework.
Yes.
Okay. Seeing this?
Yep.
So this was like my, made a mistake, but yeah. I have,
it's a hash tool.
So if I said to you, and I'll put it in the chat, but if I said to you, I have a secret and this is the hash of it, and you don't know what the secret is, you just have the secret, you have the hash with you, and then at any point in time I can reveal to anyone that my secret was 21, and you can see here that the hash computes to exactly what you have in the chat.
Yeah.
So this idea of this 21, this is what gets passed along. Everybody along that route knows the hash, but doesn't know what created it. And so the way we could have done this also is I could have like shared the hash publicly with the chat with everyone here, and then in a private, DM, I could have like emailed Steve and then given him the 21 as being the answer, and then Steve gives it to Alexa, and then Alexa gives it to Steven and whatnot.
The other interesting thing too is if you'd like change that to 22, just make a very small change. It changes the entire thing. It's a completely random or pseudo-random distribution and the hash.
Yeah.
So little
So,
changes
and the only
make
way-
big changes. Yeah, so
This,
the only way to do it is
there's a wrapping of those hashes, right? So it's like a hash of a hash of a, some like this kind of like onion concept. I read about. No.
In this case, I think it's only hashed once, but
Okay.
it's possible. Sometimes it's like they explain it as a one hash, but there's a lot of parts in Bitcoin that hash twice, and I'm not 100% sure. Like
This one is hashed twice. This is a RIPE-MD 160 hash. So it's one SHA-256, then our RIPE-MD 120 on top of that.
to shorten it. Okay.
okay.
So what if this is too long? What Raj is saying is that sometimes this is just too long to transmit. So then you take that and you put it into a RIPE-MD, which is
Maybe they don't have it on this.
yeah, they don't have it. Anyway, so it's another one that shortens it basically. So you end up with like something even smaller, but it unpacks the same way. So I wanna basically not share my screen for a second. I think I'm gonna stop sharing, and we're gonna try something. Let me just, I'm doing this on the fly, so.
Welcome, Liam. Okay, this is starting to make sense to me. So yeah, so Dina needs to give the secret to Chan, or else their contract will fall apart and she won't get her money. And then Chan needs to pass the secret that he got from Dina back to Bob, or their contract will fall apart. And then Bob needs to pass it back to Alice, or else their contract will fall apart.
Mm-hmm.
Interesting.
And the chapter here, it was just want to make sure. So they're talking about this idea of checking whether the hash equals the secret. And we're going to use the IDE to basically take a look at that. And if you look at this, I'm going to do it live, but I think it starts with SHA-256.
And you're not sharing right now, at least I'm not seeing it.
I can see it. I could see it.
Okay.
So maybe it was just. Oh, now it's gone though.
Oh, this?
Oh yeah, I can see it.
Well, if everybody else can see it, that's good.
Maybe it'll just take a minute to. This is a cool tool. I was not aware of this one.
Yeah. So what I'm doing is I'm taking this idea here of the operation or operator, I think, SHA-256, and then my hash, and then the equal operator. And so when I put all these together, when I want to basically make that script go, this is currently not going to run, right? This is just the final part of it. So if I try to do that, something's missing. I need some secret at first so that I can hash it. And my secret here, I'm going to tell you guys that the secret is 42 is my secret number. And now if I have that and I execute that script step by step, the first thing that happens, if I press on the step button here, you're going to see it appear on the stack. Step 1 is put 42 on the stack. So
that's neat.
I love it. Oh my God.
You seen that? Steve?
Yeah, I'm seeing it now. It's great.
Okay. So I'm putting 42 on the stack. My next operation is SHA-256 it and return whatever that value is. So I have this value. We're just going to make sure that indeed it is the right value by putting 42 in this, 73, 47, 5, blah, blah, blah. That's indeed what I have. That's what's being returned. The next step is to put this here, right? This hash that was given initially by, this is the hash that was given by Dina, or the secret. So I'm adding it to the stack. And then my last step is an operator equal, which will take those two items on the stack and verify that they are the same. And when I do that, it returns one last number on the stack, and it's a 1. And because it's a 1, we know that the script has succeeded. And this was because I gave, so this was me providing you folks with the 42 that you needed to make this thing work. But if I'd said, 17, or you could have tried 17, and then if you run this step by step, you'll find that when you hash it, the two hashes together don't actually equal. So
does it? Oh yeah, so it puts a 0 value.
Yeah, puts a 0 value on the stack. And so this script is going to fail until you provide the proper secret for it to fully run.
That's awesome.
So that's kind of like the screen share that I wanted to do.
This is so awesome. Thanks.
You're welcome. They go pretty cool too. And it's cool because it's you can do 1, 2, add, right? And it returns.
You are literally speaking Bitcoin.
Yeah, exactly.
Yeah,
I don't know if it's like, I haven't explored it super deeply. I don't know if it does everything or if it's a subset, or for example, they have like a really advanced a really advanced script here.
Yeah, the HTLC.
HTLC. So does that run? I assume it does, but
I wonder if it's going to be if it's updated yet to support any of the Schnorr stuff, because there's going to be some new opcodes coming up.
True that. There's a GitHub.
What is? Yeah, it looks like it's a GitHub project.
So I don't know.
Anyway, that's really cool. I don't know if it talks about it in this chapter, but one of the questions I wanted to understand, maybe they talk about it later, is so I've sent my secret all the way through all the steps, and Alice has the original secret random value. So at that point, the payment's gone through. What does Alice and everybody else along the path need to keep as a backup in case, because this is still all off chain, right? So at some point, these channels could get closed with potentially an older state. So do I need to keep all of those secrets, because that's what I'm going to use to claim my payment? Or does anybody know if they went into that here?
No, they didn't. And basically, the backup thing is complicated. I think, as far as I understand it, once Dina gets paid, the state between Alice, Bob, and Chan, these states can be in two different phases. One, that the commitment transaction holds the HTLCs, and another when the commitment transaction doesn't hold the HTLC. So when it will not hold the HTLC, when the HTLC is basically absorbed into the balances of the commitment transaction. So for Alice and Bob has a commitment transaction that gives them 2 shares of the balances. Lightning works by updating the balance of these 2 parts of that multisig, but they don't update it all the time. They just keep a pool of HTLCs, and they together like simultaneously they just agreed upon it, like at I guess like at what point they will just together settle all their HTLCs into their commitment transaction. So depending on the phase in which this commitment transaction is, the channel backup I think will be different, because when you have the HTLC you need to keep the payment preimages, because if you need to put the HTLCs on chain, then you will need those secrets in order to take the transaction from HTLC. But once the HTLC is merged into the commitment transaction balance, then you don't need to keep the payment secrets anymore. You can forget about it. You just, whenever you put the commitment transaction on chain, you get the latest updated balance.
I see. That's very interesting. Yeah, hopefully he'll go into that in one of the other chapters, but I think that's kind of from a, like if you want to understand the safety profile, understanding that stuff's interesting.
Yep.
But yeah, I guess this is the basic level of just what information is passed between parties to commit to a payment. So that's good.
Yeah, and I'm also not sure, like there may be like other things that they have to like keep up apart from this chain payments and secrets. It gets really involved when talking about like recovering channels that has been like old channel states. It can get into a lot of like problems and troubles, and it's not a straightforward thing like Bitcoin, like when you have a seed and we can derive all the addresses simply. Yeah.
Yeah. No, yeah, that's interesting. It's a very complicated protocol, but I guess that's why he's breaking it down into the simple one step at a time. And then we get the basics, we can get into that complicated stuff, more complicated stuff. Yeah, because in theory, you are sort of, you have your channel balance with your channel partner, and then you have these sort of sub channels in a way, these people that are routing through your main channel. So that's two sets of updates or states you're maintaining.
Yeah. And also like one of the with the big problem of like finding paths is like all we know about a channel is the total capacity, right? The total sum of balances on two sides. We don't know the distribution of the sum, right? And that is not gossiped into the Lightning protocol, because that will like give away who has how much of money. So because we don't have the distribution of the channel, so even if we in our graph we can see like, okay, there is a channel exists between me and somebody else which has an amount of capacity that can pass through the channel, but what if the sending end of that channel doesn't have that capacity in their part of the balance? That I don't know about. So I cannot be sure just by looking at the graph whether I should be able to pass through this channel. The only way for me to know that is to try it. So that's why like they use this probing mechanism. So they just keep trying until the payment goes through. And this was like explained in that chain code talk also. And because the Lightning network is not a stable network, it's constantly updating, right? So every payment that is flowing through the network is updating these channel balances and the distribution of this channel. So I can have this kind of situation like once I try to send a payment through some channels, I see there is a path, I try it, but it doesn't go through because the balances are not on the correct sides of it. But then 5 minutes later, there are some other payments that happen through the network that redistributed the balance. Now that payment will go through. So even if a payment fails, that doesn't mean that I cannot send the payment. I can keep try 5 minutes later and the network reorients itself and the payment will go through. So this kind of like dynamic behaviors comes into the picture of like pathfinding problem of Lightning Network, and that makes the stuff even more complicated.
On the topic of probing, isn't probing like you're essentially having to calculate the graph beforehand, and you're sending a payment that you know is not going to result in a like it's not going to be successful. It's like a fake payment, and the reason why you're doing that, yes, is to want to be able to calculate the fees and the success rate of the potential success rate of that payment going through.
No, it's not like that. It's like real payment. No, it's like real payment, and until that payment comes back to you, you have no way of knowing whether that gone through or failed. So the atomicity of Lightning Network ensures that either the payment will come back to you or it will pass through. But you don't probe in the sense like you try around and see what works and what doesn't work. You just take your live thing, throw in the network, and see whether it comes back to you or not. Until it doesn't comes back to you, you keep throwing in different paths.
Okay, so like the first step is calculating like the route and then trying the route, basically,
Yeah.
and then hopefully there's going to be a success at that point.
Yeah, and basically the route is basically two information: the public key of the node and the capacity of the channel.
Yeah.
And you basically cannot create your success probability from that information because you don't know the distribution of channel balances in that particular channel. So you might think like there are enough balance, but there are not enough balance in the right side. It's on the other side of the node.
And then one of those nodes could go offline in the meantime and all that as well.
Yeah, that can happen. Yeah.
Seems like there's definitely a hierarchy of information too, because you've got your, at the top level, you've got just your step-by-step channels, and then below that you're negotiating all these sub, transactions through you, which will then update that higher level channel. At least maybe wasn't in this chapter, but that's, I think, how you were explaining it, Raj. And then, the whole pathfinding thing. One interesting thing, I don't know if he's talked about, I guess he hasn't talked about pathfinding yet, but in this retry thing, as I understood it, there's a way you can try multiple paths through the network, and only one of them will succeed and the others will fail without having to worry about creating duplicate channels through the network. That'll be interesting. We haven't gotten to it yet, but that'll be interesting to see how it works.
But I think the problem over there is like creating and sending through HTLCs can have like a lot of risks. Like there are a lot of ways you can get stuck in your process of sending HTLC. So if you don't want to do that too many times, like too frequently, and so the reason that they just don't keep on trying like parallelly into multiple channels, why not just why convey, like why rely on one try when you can like do it parallelly? The reason I think they don't do it because there are like cases where at the point of like sending transaction, you can get into really bad situation and get your HTLCs locked, and there is no way to mitigate that. So another process is like this atomic multipath payment thing, like where you are basically like dividing your value into like small chunks and then trying each chunks in different paths. But there you get the same problem, like more channels you try to pass through, the more risk of like you getting into those kind of bad situations that they label it, that can get your funds locked. So and the idea of JIT routing is simply this, is basically instead of like trying to find like source-based pathfinding, like in current phase of Lightning Network, the entire path is directed by the source. Like Alice wants to pay to Dana, so Alice describes and creates the onion basically that will be passed through the network. So it's Alice who knows the entire path. So and it can happen like Alice the onion goes to Bob, and Bob says like, oh, I don't have a channel with enough capacity to pass through this onion. So Bob will send a failure message to Alice, and then Alice will know, okay, this thing doesn't work, so he tries with another peer. But in JIT routing, what Bob will do is like, instead of saying failure to Alice, he will say like, hey, I don't have enough capacity if any of my fund, but for you, I can rebalance one of my channel and pass through that channel. And for that, I will take a small fee. And so if he can do that, then, and if each nodes can do that, then it's kind of like very similar to our BGP network routing in proxies. Like each proxy is like, each router is trying to like do the best thing possible to transmit that network. And here Bob can do like, instead of throwing error back to Alice, Bob can say like, hey, I don't have the channel right now, but for you, if you pay me a fee, I will rebalance one of my channel so that it has enough capacity to send through this onion. And the next guy will do the same, the next guy will do the same, and next guy will do the same. So in this way, the route is not defined by the source itself. The route will get changed as it move past through the network, but we kind of like have this nice like self-correcting behavior where the payment will try to go through to the correct recipient. So these are like some cool concepts that people are working on. Really exciting.
Yeah, that's really interesting.
I feel like that would create a lot of cascading. Like you're trying to pay
updates.
one person, but then it ends up being 7 channel rebalances because everybody along that route is rebalancing, and that creates another need for another rebalance and another rebalance.
Yeah, something like that. Yeah.
I guess it could also be kind of a game theory issue too, possibly, where somebody says you have to pay me to rebalance even though they already have the capacity. Like, how do you know that they're not just saying pay me to get it through? And there might be a better way.
Nice.
You don't have visibility, but
and for that he talks about this thing called like the 5-node diameter network. Like he has described this into his paper. So what Alice needs, in order to JIT routing to work, what Alice needs to know is like Bob's balance distribution and Chan's balance distribution. So Alice knows that Bob is not lying about rebalancing, and Bob on the same hand will know Chan's distribution and Dina's distribution. They called it friend of a friend network. So you know about the friend of your friends, and in this way you know that your friend is not lying to you.
Right. So you have basically local information, and if everybody has local information as it propagates through, they can
then everybody can do the
cheating.
Best possible, or they term it like best effort basis routing. So everybody is putting in their best effort to route this packet, and probably that's the reason they call about this friend of a friend network, because you know that need to know that information in order to know that nobody's cheating.
Wow. That's
Can I
pretty
show
cool
you
stuff.
something to see if I'm getting this properly? Because, the second time you read it, you think, am I really getting it? So I'm trying to work on a little diagram. It's kind of simple. Let's see.
Oops, you've muted, Alexa.
Thank you for letting me know. So I think there's like a couple of things that I'm trying to put in here now. It's the same diagram that he has, right? It's Alice, Bob, Dina, Chan and Dina. And I'm thinking that it works kind of in 2 ways, right? It's first when you kind of send the money in, and then when everybody kind of, it's like kind of on the outside, you get it back. And there's some protections here, right? So you send the hash, and then the money gets locked into escrow, and there's a time lock attached to it. And that helps with the atomicity of it. But, and then once kind of the, what is it called? The secret is released, or the receipt, and once the money kind of makes it through, then this is where you need kind of the digital signature so people don't spend it like on the way back, or is it all the time? Or did I just make it more confusing? Okay.
Well, it's not sending digital signatures, right? It's sending the R secret from Dina back to Alice.
Yeah, but it's attached to a digital signature because they don't want to. They want to prevent spending somehow.
I guess that's in the messaging then. That must be in the Dina to Chan. There must be maybe a signed message. I don't know.
Is it?
There will be like a lot of digital signatures, not just one. And they will, like Dina and Chan will be communicating probably for a single payment 2 digital signatures depending on their different version of commitment transactions. So it will be a little bit hard to track it through digital signatures because they are like a lot of digital signatures all over the place, and it's not like they are just one signature that will pass through for a single payment. There will be hundreds of signatures throughout the network that will be involved through for that one single payment. So maybe like one thing that is clearly coming back from Dina to Alice is like the R secret, like the green box. Right, that green box is like Dina sends it to Chan, then Chan says like, okay, I got the green box, let's settle our HTLCs between me and Dina. Then Chan will send it to Bob. Bob will go say like, okay, I got my green box, let's settle back with Chan. Then Bob will send it to Alice. Alice will say like, okay, now I finally got the green box, let's settle to Bob. And once Alice got the green box, the payment is completed. Alice matches like, okay, the Dina told me like the green box will match to this yellow hash, that matches, so Dina must have been paid, my channel is complete, this HTLC is done. And then Alice basically says Bob like, hey, like this HTLC, remember, this is the preimage, this proves like this is the green box, this proves like this payment is complete, why not like take this balance and put it into our commitment transactions. And that's what settlement means in Lightning Network. They just absorb the HTLC back into their commitment transactions to outputs.
Okay, so it's the R that's coming back, and but you know, part of the chapter deals with something like where it says that it needs a specific digital signature with a public key. I think that's what it says, with a public key, each individual.
Yeah, if you go to that script, the HTLC script, that shows like exactly where signatures will be required. So you can calculate like how many signatures will be required in an HTLC script. And I think that's like
I think the digital signature part is kind of like a side helper piece. I don't know that it would, in this, like the diagram is an abstraction away from that I think this is a good way to do it, better than to include the digital signatures. Because the digital signature says, the problem with this right now is that the R is the same for everyone. So if the secret is the only thing you need to unlock the funds, then you could unlock everybody's funds. You could just like, as soon as you know the secret, you could grab it all. But that's what they explain. And so rather, it's this requirement that they have is two things. It's the secret plus a payment at this particular address. But that's kind of like a...
Yeah, and I think like the digital signature part goes into this orange box locked in escrow. So whatever the detail of that locked in escrow is, that contains all the digital signatures to ensure that nobody cheats in the network.
Okay, thank you. I think that answers my question, because I wasn't sure if it was something that was needed on the way back, you know, and just on the way back. So it's something that always gets shared then.
Yeah.
So we're kind of approaching an hour here. I'm going to go ahead and turn the recording off. You know, keep an eye out on the Bitcoin Design Calendar, everybody, for the next meetup details. We can all keep talking here, but I'm going to go ahead and end the recording here.